Every electrical consumer generates feedback from the grid, whether during normal operation or when switching on and off. This grid feedback causes a distortion in the grid electricity that does not meet the specified in technical requirements. So what does this mean for the grid operators? Malfunctions, thermal overload, or total failure of the production plant may occur. At the same time, the insurance and guarantee protection expires. In the worst-case scenario, people may even be affected by the damage. Therefore, the plant operator is obligated to guarantee, record, and document the specified quality of the grid. Now, let's take a look at the entire situation in more detail. We will take a frequency converter as an example. This shows the typical rabbit ears in the electricity curve. For this we draw a simple graph, and in the first step we plot the voltage sign. It may not be perfect, but it looks like a sine wave. U is for voltage. Now the electricity curve of the frequency converter. As I mentioned before, the rabbit ears are characteristic of this. Well, not exactly ideal, but I think you can see where I'm going. The blue curve I is for electricity. In the next step, I will explain in more detail how the active filter works as a part of the block circuit diagram. The first position is the grid. And connected to that grid is our consumer, in this case the frequency converter. With the motor. Frequency converter, motor. In the next step we add our storage system with the active filter. Here we have our test volt PCS. With the test volt battery connected. In order to examine more closely what is actually happening, we will use some virtual grid points to look at the consumer, the storage system, and the grid connection point in detail. We assign these measuring points to the consumer, the storage system, and finally, of course, to the grid connection point. But in order for the inverter and the active filter to work correctly, the inverter must have a measuring point at the grid connection point. This is achieved by using a separate measuring point for the inverter. It then measures the grid electricity and counteracts it if necessary. In a first step, we apply the simplified depiction of the electricity curve with the rabbit ears at the grid connection point, since the frequency inverter generates this electricity signal. I've exaggerated this just a bit here, but you should be able to roughly visualize it in that way. This means that this current sign, which does not meet the technical specifications, is also present at the grid connection point. This is not permissible. But what does the TV PCS now do with the active filter? It measures the signal and generates a reverse signal, a reverse current. We know this from noise-cancelling headphones, for example, which work according to a similar principle. So, the load current that does not meet the normative requirements is superimposed with a compensation current through the TV PCS. This is the compensation current. A compensation of the current occurs if these two currents are superimposed. And at the grid connection point, there's now a current sign that meets the normative specifications. This means that a clean current sign is generated from the signal with the help of the test volt PCS. To clarify this point, I will simply redraw the result. Here we have our voltage sign. It hasn't changed much. And now we have a current sign that is not quite ideal, but it meets the normative requirements. So, once again in detail. By using an active filter, an unclean current sign becomes grid electricity that meets the standards. What are the benefits of the power quality application for the customer? First of all, it protects their guarantee claims against the plant manufacturer with respect to the power supply. Secondly, it reduces downtimes and standstill times of their production plants caused by fluctuations in voltage. And thirdly, it meets the technical requirements according to DIN regarding the quality of the power grid.